Today's presentation is titled Discovering Neptune and Disproving Vulcan. I wanted to point out I've also got a subtext to this, which is solving discrepancies between theory and observation. To me, this topic of Neptune and Vulcan are parts of a puzzle, and that it has been going on for quite a long time. In the 2nd century, Ptolemy came up with the concept of an Earth-centered solar system. And in order to explain it, it got to be quite complicated, as illustrated here. Those are the outcome of the cycles and epicycles that Ptolemy used to explain planetary behavior. In the 16th century, that's almost a millennium and a half after Ptolemy, Copernicus came up with the idea that no, the Earth is not the center of the solar system, the sun is the center of the solar system, and thus we get that representation here. So the Ptolemaic view had been the subject of lots of discrepancies and modulations along the way. So in this case, Copernicus presents the solution that then solves a lot of those problems. Technology was developed by people like Galileo starting in the 17th century that would vastly improve astronomy that had existed before, which had relied primarily on visual, eye visual examination of the sky. As those tools developed, folks came along like Bray, who collected a lot of data, which was then handed off to Kepler in the 17th century for the development of his 3 laws of planetary motion. The one that's primarily of interest here today is the 2nd law, which basically gives you some idea of the velocity of a planet around the sun at various points in its orbit. As it's closer to the sun, of course, it goes faster, and as it's much further away, it goes slower. Newton then built upon the work of Kepler, and amongst his works, of course, are the 3 laws of mechanics, but also the universal law of gravitation, which is illustrated here. Of course, the important thing to consider is that we need to know the masses of the 2 entities involved, and we also need to know their separation. And of course, this is subject to the inverse square law. So further away, the less the gravitational forces are. In 1781, William Herschel and his sister Caroline discovered Uranus by accident. By accident, I mean they weren't necessarily looking for it, but they spent a lot of time going over the data that had been collected up until that time. And amongst there, they noticed what appeared to be a planet. And eventually it was agreed that this was a planet, and it was then targeted by other astronomers for viewing and observation, which they found out that this nice, pretty representation here to the right is not really the way that Uranus moves, and that it has some strange behaviors. That the speed, for example, is not the way that it had been expected to be. Noticing that discrepancies and that it was not behaving, people had to come up with some potential solutions to that. And the best solution of the time that one come up was that there was an 8th planet exerting gravitational influence on Uranus. So the search began. This is just an illustration of how planetary motions or how planets affect each other's planetary motions. The yellow orbit on the center is the one where the planet existed, in this case Uranus, prior to getting close to another planet, in this case eventually became called Neptune. And in this case you see that the orbit is slightly perturbed, and in fact it moves out slightly because of the gravitational attraction between Neptune and Uranus. So it gets into a larger orbit, and we know from Kepler that means then that the velocity has gone down, and thus the change in momentum has also decreased, as indicated slightly by maybe probably in exaggerated fashion by the two colored arrows there. So these attractions, of course, are quite complicated. The gravitational attraction, of course, builds and then it subsides as the planets come in juxtaposition to each other. But the laws of Newton and Kepler are at the heart of trying to figure out those interactions. In 1846, Urbain-Le-Verrier calculated the expected position of Neptune. Now, I should point out that he wasn't using directly the universal law of gravity in doing that, but since the measurements are based off of observations from Earth, there were techniques that had been developed to explain the situation and the likelihood of certain observations being made. And that was the basis of Verrier's work, as well as there was a British scientist, J.C. Adams, who had come to a similar conclusion just a bit before. And his only fault was that Le-Verrier managed to get his work confirmed and published before the work of J.C. Adams. So in fact, upon completion of Le-Verrier's work, he pushed it off to the observatory in Berlin, and it said, of course, I don't have any verification of this, but 30 minutes after the astronomer there received the calculations, they found and identified Neptune just where Le-Verrier had expected it to be. What's this significance for us? Well, for one thing, it confirms that Newton's law of universal gravitation actually works as it was proposed to do, and that both Kepler's laws and Newton's laws were not just models, but could have predictive capability. But as I said, not necessarily just exactly as we would have expected in our bird's eye view of the solar system, but from the perspective of an observer on Earth. However, I dragged this quote out from J.C. Adams in his published work at the time, basically saying that the law of gravitation was just too firmly established to believe that there was anything else. And that's why they went off down the path that they did in looking for this eighth planet. The second discrepancy that we're going to talk about is disproving Vulcan. Here you see a representation, an artist's representation of Mercury's orbiting around the sun, and the fact that the orbit itself precesses over time. This had been noticed as early as Newton's time, that the orbit of Mercury was precessing. To explain this precession with Newtonian mechanics, Le-Verrier, of course, having been successful with Neptune, came up with the idea that this precession was being caused by a planet that was closer to the sun than Mercury, and people went looking for this planet. In fact, a number of people proposed that they had seen it, although the problem was that they never seemed to see the same planet. But in 1859, Le-Verrier reported that the object had been observed. He didn't observe it himself, but he reported that it had been observed, and the planet was eventually named Vulcan. Only one problem, even after having named it and done a lot of calculations on it, the situation never really resolved itself, and his calculations on the precession of Mercury always left a magical 43 seconds per century unaccounted for. Astronomers are great in the details. However, in 1916, Einstein came along with his theory on general relativity. Before he published, he realized that he needed some observational proof for his assertions about space-time and the curvature of space-time around large, massive objects. And there were several different possibilities that were open to him, but only one actually had observations that were available in 1916. Some of the others would be coming shortly thereafter, but that one was available in 1916, and that happened to be, of course, the precession of Mercury. There was lots of data about that. Einstein, this is the top part of the diagram here, is actually an extract from the entire section in the General Relativity publication that talks about Mercury and the precession problem. And in the middle of this, you'll see the actual formula that was used by Einstein, and underneath I got a Google translation of the text that is below that formula, which states that the calculation gives an advance of a perihelion of 43 seconds in 100 years for the planet Mercury. So it's right on target for the gap that had been developed through strictly Newtonian mechanics. So this was a great thing for Einstein, and it resolved, of course, this big mystery about why Mercury was behaving in the way that it did. And it also was, of course, a great thing for Einstein himself. And it was he actually had data to show the confirmation of his theory. Now, so Mercury resolved through Einstein. Neptune resolved the problem with Uranus through Newtonian mechanics. But in 1931, George Lemaitre published the Big Bang Theory. So I just want to follow up with one more example just to wrap around the other two. As you know, the idea is that there was a singularity that exploded and has been expanding ever since. But the theory, of course, is that gravitational influences would eventually pull that back in, and it would go into a collapse, back to a singularity, and then potentially a bang, bang, bang kind of thing would happen over time. But that was thinking in most of the 20th century. However, the Hubble Space Telescope was launched in 1990. A lot of data was captured during the first years of its observations in the 1990s. But by 1998, there was enough data that had been collected that showed that the universe's expansion was actually accelerating and not slowing. It was maybe had been slowing, but it was actually accelerating over time. And of course, that was a discrepancy with the thinking that had been developed all throughout the 20th century. There needed to be an explanation for this, and eventually dark energy was brought into the picture to be the explanation and to resolve the discrepancy. Some references here that were used in the preparation of this presentation. Thanks for your attention.